And once again, Holden, you have an alibi.
An alibi for what exactly?
Well, you're being videoed, they're actually being here at this time. They, on the other hand, can claim that they were here.
I'd vouch for them.
Actually, would you whack the thing up? Oh, sorry. Oh, got that on.
Oops. Okay. Now?
Yeah.
I don't know if I hit it
That's
well. I can hear.
Yeah, so it got a little bit louder there.
Yeah. Here, hit it again.
Oops. Did I hit? Maybe I should try again.
I heard this one.
Yeah, I heard it more the first time.
Let me try again. Whoops. This is the first
Seems
time.
like.
I think this is
All
the
right.
first time I've used a tuning board too, so.
All right, so let's do it differently. So, do it, instead of having to hit here, smack it and then just hold it over like that.
Yeah.
Okay.
And if you need to smack it off to the side and then put it over. I need it louder.
Here we go.
Smack it again.
I heard it.
Yeah, that's a false one. That's what I was talking about.
There we go.
So somewhere around the 78.
Yeah.
Let's see if we can get that false again. Smack it again.
Now I see how these things work. It's best to hit it, hold it up and hit it from the side. And also make sure to keep it.
Yeah, just not hearing it.
Probably ghost harmonics.
All right, so let's try it with a higher frequency.
I have a question.
Yes.
On this instrument, this one,
The tuning fork.
so is the frequency of the top one different with the middle one? Is it different, I want to say? Because the top one will move faster than the middle one.
But they should still be vibrating back and forth at this
It's the same.
together. So the frequency would be the same.
Oh.
But that's why I was having this part though over here, because this will vibrate more. It'll have a greater amplitude, therefore will have a greater pressure difference.
Yeah, you can see it,
Yeah,
it's kind of blurred a bit.
Can't really see him vibrating. I couldn't see him until I see him now though. I was talking about when you were hitting the top of the
All right,
tube holder there.
this is 512 hertz. It is a higher frequency, and as you can see, a higher frequency would mean a shorter wavelength, which means that the resonance should happen higher up. See how well it goes. That's the primary one. That's the one we wanted.
Hit it again.
Yeah, let's get this thing up and.
Let me fix this thing.
I guess not really hearing those, so, apparently I'm making stuff up.
What if we used, an actual do we have an actual hammer?
Don't bang metal on metal as much as you can.
Oh,
I was thinking that too, but
Yeah, you get a much louder sound if you do metal on metal, but then you start getting, if you notice the difference between
deformation,
the two tuning forks.
yeah. One's beat and one's not.
Yep. From people banging this thing on.
Everything.
Yeah. And it sometimes happens with that. I mean, sometimes you miss with the rubber stopper and it gets metal on metal, but, you know, let's try to minimize the amount of times that happens. All right. So that was around 14, you said?
Yeah,
Plus the 2, so it's somewhere around 16 centimeter.
alright.
So let's find out what the prediction is.
What frequency did we say that?
512.
12.
So what should the length be based upon that?
Assuming I did it right, 0.671.
Yeah. 0.671
All right, that's the wavelength.
meters, yeah.
And so we should expect to hear the first harmonic at what air height?
So it's about 16 centimeters. It was 0.168 meters.
0.168?
Yes. Meters. Plus the 2. I said 14 plus the 2 is 16. So we're-
Yeah, so we're close.
yeah.
You can also flip this around, given different stuff. I think the lab that I eventually have come upon for this is you do different frequencies, find that first harmonic for different frequencies, find the first harmonic for the third harmonic for the same set of frequencies, and do some plots. And so, based on L, we find wavelength. We know the frequency, and so in essence, solve for speed based upon the
Temperature.
speed of air, or speed of sound in air will be related to the slope of the graph.
Sweet.
And as any instructor of physics always hopes, the results actually come out better than the older version of this lab, which I'm hoping you will never see. All right, so what have I forgot? We've done that, we've done superposition, we've done the harmonics, we've done sound. Back to that, air columns, we've done that.
What chapter are we on?
This is chapter 22. All right. Turn it 12, 20, okay. Questions up to here?
So what are we doing now, Doppler effect?
Yep. introduced Doppler through a video. I've looked up videos of, there was a guy who put up some microphones on a road, and had people honk their horns as he went past I figure out if that thing's coming on or not. The light is blinking, but.
Yeah, it's blinking green.
There we go, got some sound. There we go, that's the one. Thank you. Oh, I should turn the speaker off. You can also get the light, please.
The Doppler effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
multiply the other bit. Okay. So you all understand Doppler perfectly now?
I heard some theories that the redshift is due to the stretch of the space rather than the moving star. That space is stretching out, and the farther the star, so the light will have a shock the frequency.
If it's coming towards us, or if we're approaching each other.
Yes, but due to the space is expanding. Some theory that the space is
Oh.
expanding, and farther star away from us, and the light will when the light reach us, and the frequency is different due to the stretch of the space. That's a theory I heard on the internet.
That the universe is expanding?
Yes.
Yeah, and I mean, the reasoning behind that is, if you think about, if everything started in the Big Bang, so at one point it was all concentrated, and then it sort of blows outwards. So imagine a balloon. As you blow a balloon up, if you take 2 points on a balloon, if you keep blowing up the balloon, those points get farther and farther away from you. As a matter of fact, almost every point on that balloon gets farther and farther away from you, or from wherever you are on the balloon. And so that's the idea. And the big question is, will it get to a certain point and stop, and then come back and crush into itself again, known as the big crunch, or will it just keep going on forever? And the way it's looking right now is that things seem to be speeding up as they're moving away. So it's right now, the thinking is that the universe will just keep expanding, and at some point from Earth, not that humans will be here at that point, but from Earth you will look out and pretty much not see anything.
It would just be a huge version of the Booty's void.
I mean, isn't there a black hole in the center of our galaxy that we're slowly spinning into? Sort of.
No, I think it's pretty stable at this point. The fact that I have not heard that we're getting any closer or any farther away
Oh,
from
I
it.
didn't know either, I just thought that was my understanding.
I think it's like our relation with the sun. Maybe, I don't.
The difference is with the sun, well, one, we can see our sun. We can't really see the black hole in the center of the galaxy, it's just speculated. But as our sun starts burning up its fuel, it will start to expand.
Oh, right.
And our sun is not so massive. Generally, you've got two things going on. You have this gravitational pull trying to keep everything in, and then you have this external pressure coming from the nuclear reactions that are going on, pushing radiation outwards. And so we get this nice little balance there going on at this point in the life of us and the sun, which is good for us. And as it starts to run out of fuel, it's burning through mass. Mass gets converted to energy, gets sent out. We enjoy the warmth from it. But our sun has not enough mass for it to collapse in on itself as the radiation pressure drops off. What's going to happen is our sun will just keep expanding. However, when I was growing up, or middle school years, they kept saying at some point, we're going to be consumed by the sun. Well, no, we won't, not according to the theories. What's going to happen is the sun loses its mass, the gravitational pull on us will be less, and so we will move farther out.
Oh.
The idea is eventually the sun will be here, but the earth will not be. The earth will be farther out. But by then, humans aren't expected to be around anyway. So, not that we'll know. Matter of fact, if you look at any astrophysics, it is always amazing to me. Think about the size of the universe. We're on this tiny little speck, in a tiny little speck, in a tiny little speck of the universe. And the fact that we can draw any conclusions at all is just mind-boggling.
I can understand why I can understand where some of the existential dread comes from too, because it, just like because like you said, we're on a spec, which is in a spec, which is in a spec universe, as we know it is so large, and we're tiny,
Yeah.
absolutely tiny. It somewhat unnerves me a bit, but.
I find it very humbling, especially driving at night when you're outside the light pollution.
Oh, yeah.
And you just look up and you're thinking, wow,
Yeah.
I
Yeah.
am insignificant.
When you're in the middle of the Atlantic, there's no light pollution, so you can see the
Oh.
whole thing.
Oh, you were in the Navy.
Yeah, so you can clearly see the Milky Way at night. It's pretty awesome.
Oh, it is. There's been a couple times I've been in situations to clearly see the Milky Way. It is
Yeah,
on
And
fire.
sometimes there's no light and you can't see your hand in front of your face when you have it this close. It's that dark.
There was a scene from the movie, A Bridge Too Far, but then I was listening to the book that it was based upon, and it was in the book too. Not just Hollywood, but they had a scene where where Americans just came into a town and they were walking along and they thought they joined another group of Americans and realized that they were Germans. Then they were Americans and Germans walking together, not realizing that they were from the other side
Yeah.
at that moment, just because how dark it was. Sorry, I shot off on a tangent.
That's okay.
Well, it's an informative tangent nonetheless.
All right, so what we need to do now is, because it's physics, derive a formula. Because that way you'll feel a little bit more complete. So what's gonna happen here is I've got an object here, which we're gonna call source. Emitting sound. So it's emitting sound waves at, there's some amount of time in between the sound waves as they are emitted. So sound waves are just moving outwards. And then I'm gonna put an observer here. Who's gonna get these sound waves. So if the source and the observer are not moving, then the frequency with which these are released should match the frequency with which the observer gets hit. So imagine that you've got a very still lake, you throw a rock into the pond, and you get the ripple going in, and then some set time later you throw another rock and you hit in the exact same spot, so you get another ripple going. And then the exact same amount of time later, you throw another rock and you get another ripple going. So these waves are gonna be moving out, and then if there's a bug sitting on the water, it's gonna get hit by these with the same period with which you threw the rocks in. However, as in the demonstration, as if the source moved closer, then that first wave, well, the first wave, let's see if I can go back to my classic horrible animation here. So I have an object giving off sound. So that sound wave is centered right there where it was emitted. But by then, this object has moved. So these are 2 moments in time, third moment in time down here. So that first wave is now expanding out, so if it went that far the first time. So that first sound wave is now out to there. The second sound wave was emitted at this point right here. That's the center of the second pulse. And so you can see, especially the way I drew it, that the wavelength here is much smaller than the wavelength here. The speed is the same in both cases of the wave. And since speed is frequency times wavelength, then frequency is speed over wavelength. So as the wavelength increases, the frequency drops. As the wavelength gets smaller, the frequency increases. And so that's why as the car comes towards you, we get that, and then it drops off. So the higher frequency, the lower frequency. Sorry, occasionally I get these moments where I feel like I have to breathe fresher air. Man, I look forward to this pandemic ending. So what I'm going to do is look at the relationship between the frequency of the source and the frequency of the observed. So an object is here, so this is my source, and it is moving with some speed v. So at time is equal to 0, it emits that first wave. So at whatever the period is, so some time capital T later, the source is now here, and that distance that it's traveled is v times t, this speed times time. But the sound wave would be here, and so we have the speed of sound times the period. This period here, I do need to add another subscript here.
T prime?
I hate to do this to you, but I'm going to, instead of source, I want to use S for sound. So I'm going to change this to emitter and the observer to receiver.
Actually, that's,
And so C sub S is the speed of sound. And so this period here is the period of the emitter. So T sub E, and that's V sub E. So at this point right here, after this period, the second sound wave is emitted. So the wavelength on the front side is that. That's the wavelength that will be received, so theta or lambda sub r. Because so if I've got some person over here being hit by the sound waves, that is going to be, he's going to get hit by the first one, then he's going to get hit by the second one, and that's the distance apart between the two. Once it's emitted, it's both wave fronts are traveling at the same speed once it's emitted. So the wavelength as measured by the receiver is just the difference between how far the first wave went and where the person was when the second wave was emitted. So this would be the speed of sound times the period emitted by, the period from the emitter's point of view minus the speed of the emitter times the period from the emitter's point of view.
Do the time from the emitters cancel, or?
We're gonna factor it out, not cancel it though. So this is CS minus VE times period from the emitter. The wavelength, let's go back to our classic relationship that the speed is equal to the frequency times the wavelength, and the relationship that frequency is 1 over the period. So this lambda r should just be the speed of sound divided by the frequency. So this is the speed of sound divided by the frequency from the receiver's point of view. This period from the emitter's point of view would be CS minus VE times 1 over the frequency from the emitter's point of view. And so the frequency that the receiver hears, solving for FR, well, I'm going to bring FE over to the other side, so this becomes FE times the speed of sound over this right here. Writing this slightly differently, if you don't see the step from here to here, this becomes CS over FR. It's equal to CS minus VE over FE. I have two fractions equal to each other, I can always move things across the diagonal. So in essence, I took my FR and brought it up. I took the FE, brought it up to the other side, and the CS minus VE I took down. So I ended up with FECS over CS minus VE. So just a quick plug and chug. Let's go to our 440. So the emitter is emitting a sound at 440 hertz. So the frequency of emission, 440 hertz. It's in a car cruising towards somebody at 30 meters per second. So the speed of the emitter, 30 meters per second, roughly 63 or so miles per hour. So what you would hear if you're on the side of the road as it approaches you, frequency received will be the frequency emitted times the speed of sound. We'll just go with 340 over 340 minus 30. So that's 440 times 340 over 310.
Uh, 482.6 hertz.
182.6 hertz. So the person in the car in my scenario here is hearing 440, but you on the side of the road are hearing 482.6. A quick double check is I know that because it's coming towards me, that the frequency I should hear will be louder, just because I've experienced it in real life and also the math works out. That was the principle that we had, was that it approaching. Once it passes me, I know I should get a lower frequency. Well, if coming towards me, I'm subtracting negative VE, then going away, I'm going to add it. So going away, this will be 440 over 340 over 340 plus 30. So 440